review on a paper called Addressing the Straggler Problem for Iterative Convergent Parallel Machine Learning Algorithms. Next slide. The exact title of the paper is Addressing the Straggler Problem for Iterative Convergent Parallel ML. And this paper was written by the following authors. This paper is written by the Carnegie Mellon University professors in collaboration with various students. Let's go to the next slide. So, what is the straggler problem in distributed iterative ML systems? So, in distributed iterative ML systems, data is split into chunks and processed at various nodes, or you can say workers. Um, these nodes must synchronize in order to share the results that were processed at these different nodes and to get the final collective output. So, but the runtime for each node varies. So each node has different computation times. So this often results in some nodes being faster and some nodes being slower. So in this environment, this often results in faster nodes having to wait for the slower nodes to finish so that they can synchronize. So such nodes or workers that slow down the task are termed as stragglers. Next slide. So is this an important problem? I think this is an important problem because when there are stragglers in the system, the faster nodes have to wait for the slower nodes, causing it to waste its resources. So the system is as fast as its slowest node due to this synchronization barrier that it has. Even in a high architecture designed for high performance, even tiny variations in computation times among nodes spawn straggler nodes. So this is a major problem that we are facing in iterative ML systems. So let's go to the next slide and see what are the current solutions to this. So these were the approaches that were used in the paper to compare the author's solution to the problem. In fact, these are the more popular approaches we found, which are used for large-scale distributed iterative ML systems. So the first one is BSP, which is short for bulk synchronous parallel. This is one of the earliest approaches to tackle the straggler problem. One approach of BSP is to identify the stragglers and blacklist them and not assign them any more work. So we don't interfere with the work that's already doing, but we don't assign more work to these blacklisted nodes. Another approach of BSP is to assign the same chunks of data to different machines. So having redundant processes running at different nodes. So they're basically racing for completion. And only the result from the faster node is considered and the redundant copies are discarded. So these are the two. This is the BSP. Let's go to the second one. It's BSP-RR, which is a variation of BSP, but with the feature of rapid reassignment. So in this approach, the straggler nodes redirect the portion of their work to the faster nodes to balance the time and resources. So the third approach is SSP, which is short for stale synchronous parallel. This approach loosens the synchronization barrier of BSP. So by using this, the nodes are able to continue with the next iteration without having to wait for other nodes to synchronize. But however, there's a limit to the number of iterations a node is allowed before it has to synchronize. So this limit is called the slack limit in SSP. Let's go to the next slide and see the newer solutions for this. So one of the most interesting solution for this is an approach called MapReduce architecture. It was originally developed at Google to process large amount of data in a distributed fashion. And Hadoop is an open source implementation of MapReduce architecture. Hadoop uses a concept called speculative task cloning, wherein Hadoop scheduler starts redundant copies on the same of the same task in a faster machine based on its heuristic comparison between each task's progress and the average task's progress. So the faster nodes no need to wait or sit idle. And also the tasks that run on Hadoop are important and stateless, and they're isolated. So this eliminates the strict synchronization barrier, just like a BSP, allowing process to go to the next iteration without having to wait for other nodes to synchronize. However, they eventually have to synchronize before they run out of resources. But it does not have the strict synchronization barrier like a BSP does. Let's see what the limitations are to the current solutions in the next slide. Okay, so for BSP, blacklisting process is a really fragile process because a fast node with just few moments of a downtime can be identified as a straggler. So this leads to wastage of resources, especially a fast worker, because you're not making use of a fast node by misidentifying them as a straggler. And running redundant copies of the same task on different machines is resource heavy. Almost half of the resources are being wasted on running redundant copies because uh, the redundant results are being discarded. And moreover, there is no guarantee that both the machines running redundant tasks are not stragglers. The limitation for BSP RR is although rapid reassignment allows straggler to offload some of their work to faster nodes, BSPRR still suffers from the synchronization barrier because the fast nodes still end up waiting for or processing redundant copies of the same data. So the number of iterations that are allowed are limited in SSP. So stragglers can still cause the fast nodes to wait for the slower node when the difference between the slower and faster workers' computation time is huge. So that times the during those times it leads to more stragglers. Let's go to the next slide. Okay, is author's motivation convincing? Yes, I think the author has convinced us, giving us various examples and showing us that a good straggler mitigation technique must utilize the minimal required resources and with the least synchronization barriers so that the system is running most efficiently. So let's take a look at the author's proposed solution to this problem in the next slide. Uh, so FlexRR is the name given to the author's proposed solution. So FlexRR short for flexible synchronization barrier with rapid reassignment. It provides parallel execution and shared state management for iterative ML systems. FlexRR combines the flexible synchronization barrier of SSP with rapid reassignment part from the BSPRR, as we've seen earlier. And so the main advantage of this solution over others is even if the gap between the faster and the slower node is huge, because of the rapid reassignment, it assigns the work from slow workers to the fast workers to strike a balance in terms of the computation time and system resources. Uh, the idea the author employed in the solution is not original because these have already been there for some time now. But it's very interesting to combine the SSP with a rapid reassignment feature from the BSPRR, and get the maximum utilization. And FlexRR support for SSP is similar to the recent systems, but its scalable data-centric mechanism, which you'll learn, is quite new in this coming slides. Okay, let's go to the next slide. Okay, let's look at the rapid reassignment design from FlexRR. So let me explain you the general idea how FlexRR works. So workers in the system exchange their progress report in a peer-to-peer mode of communication. And then upon receiving the reports, it uses an algorithm to know how far ahead or behind is the worker with respect to the other workers. And this in turn helps them in identifying who are stragglers, and stragglers then reassign portion of their work to the potential helpers. Let's look at more details into the design in the next slide. So worker groups, FlexRR uses the concept of grouping workers. Each worker is assigned to a group of workers that are eligible to provide assistance to, and this group is called the helper group. So when a node realizes that it's a straggler, it will reassign part of its work to one of the nodes from its helper group. So each node sends its progress report only to its helper group instead of broadcasting the entire network with progress reports. I think there's a really smart decision, and it can also result in a waterfall effect because in cases where a node which is helping a slower node in turn delegates some of its tasks to its helper group, causing a waterfall effect to balance the work. Let's look at worker communication. FlexR uses a non-blocking message passing interface for the workers to communicate with each other. Uh, each worker keeps a runtime to track the duration from the beginning until the synchronization point, and each worker sends progress report containing the progress iteration number and the runtime timestamp. Let me explain you with an example how rapid reassignment works in the next slide. Um, so we have three nodes here. One node which is faster than the mean average, one node which computes slower than the mean average, and one node which is running at the mean average speed of all nodes. So after completing a certain threshold progress, the fast worker sends progress report to its helper group. That is OK and slow here. And after receiving the progress report from the fast worker, the slow worker computes a comparison algorithm to find that it's lagging behind. So the slow worker then sends a do this message to reassign part of its work to the fast worker. But the fast worker finishes its job and then sends a begin helping message to the slow worker, indicating the slow worker that it is not available to help. Then the slow worker sends a do this message along with the work assigned, so that the fast worker can work on the new work that has been assigned. And now Tejas will explain the rest of the presentation.
Hello everyone, I am Tejas Ramani and I will explain next few slides beginning with rapid reassignment actions. The authors have described five primary rapid reassignment actions in FlexRR, which are designed to distribute workload from slow workers to fast helpers. The first action is identifying stragglers, and it uses algorithm for progress difference calculation. In the paper, they have given this algorithm. After reaching the 75% progress completion checkpoint, worker sends out progress report to other workers in its helper group. That report contains additional information such as number of iteration and local time in a runtime timer. After applying the progress difference calculation algorithm, the result would inform how far ahead or behind as a percentage it is relative to the progress report sender. If the workers fall behind by more than 20%, which is the default threshold, it identifies itself as a straggler. The second action is reassigning work. If a worker finds itself fallen behind the sender by default threshold of 20%, or in other words, if a worker is identified as a straggler, then it sends an initial work assignment in a do this message back to the sender. This message contains the current iteration number of the slow worker, beginning and end of the work assignment, and a local timestamp of the message. The straggler then reassigns work starting from the end of its current iteration, as it is the least disruptive point. And it also takes advantage of robustness of machine learning algorithms to process data in any order despite data dependencies. The third action is helping with work, where worker checks for do this messages on every message check, and upon receiving this message, it will compare timestamp and current iteration number. And according to the algorithm for helping decision, the worker will decide about if and when to provide assistance to the stragglers. Next, fourth action is assigning additional work, and it addresses various balancing concerns. Workers are given small amount of initial work followed by a larger amount of additional work. After a worker sends out do this message, it will check for begin helping messages. If it requires more help, then it will send another do this message to faster workers. Next, final action is canceling work reassignment. This step basically ensures that a slow worker that needs help does not start working on something which is already assigned to another fast worker. When a slow worker sends out do this message, it will check for begin helping messages. If the slow worker has not yet received begin helping message and it requires more work, then it will send out a cancel help message and finish the work itself. Next, implementation. The authors have described six cluster setup. Instances in each clusters are connected by 1 Gbps Ethernet connection. Cluster A contains 16 virtual machines running on a dedicated 16 physical machines, each with two quad-core Intel Xeon processor running at 2.66 gigahertz, and each VM runs on one physical machine with 8 CPUs and 15 GB of RAM, and they all are running Debian Linux OS. Cluster B has 64 Amazon EC2 instances, each with 8 CPUs and 15 GB RAM, and running 64-bit Ubuntu server. Cluster C is also 64 Amazon EC2 instances, but it has a lower class version of cluster. It is basically a lower class version of cluster B. Yeah, each instance has four CPUs and 7.5 GB of RAM, and they all are running 64-bit Ubuntu server as well. Cluster D contains 64 Microsoft Azure A4 standard instances, each with 8 CPU and 15 GB RAM, and they are running 64-bit Ubuntu servers on Intel Xeon processors. Cluster E has 64 Microsoft Azure A3 standard instances, each with 4 CPU and 7 GB memory, and they are running 64-bit Ubuntu server on AMD Opteron processors. Cluster F is a probe gnome dedicated cluster of 128 high-end computers. Each machine contains 4 quad-core AMD Opteron CPUs, that is 16 cores per machine and 32 GB of memory, each running with 64-bit Ubuntu server. Uh, for evaluation, primarily cluster A is used for most experiments, and other 5 clusters are used to experiment with naturally occurring stragglers in 2 public clouds. Authors have described that every experiment was run at least 3 times and they reported arithmetic means. In experiments that had injected stragglers, the first run was conducted from smallest delay injections to largest. The second is in reverse order, and the third in random order. And, the authors have done application benchmarks by 3 popular ML applications: matrix factorization (MF), second is multinomial logistic regression, and third latent Dirichlet allocation. Next, This slide shows results of experiments performed in Amazon EC2 instances. Both figures here, the charts, they show comparison of MF and LDA performance on EC2 on cluster C and cluster B respectively. Using VMs in cluster B, FlexRR reduces time per iteration by 35% for MF and 34% for LDA relative to BSP. This reduction is 25% for MF and 15% for LDA respective to SSP. Using VMs in cluster C, reductions are 53% for MF and 49% for LDA relative to BSP, and 39% for MF and 32% for LDA relative to SSP. This slide has results of MF for same experiments on cluster D and cluster E, which are basically in Microsoft Azure. Using VMs in cluster D, FlexRR was able to reduce time per iteration by 43% relative to BSP and 32% relative to SSP. In cluster E, this reduction is by 56% relative to BSP and 38% relative to SSP. So, in conclusion, authors have performed their experiments on multiple clusters having multiple instances and proved effectiveness of FlexRR. So, we think they have not only achieved what they set out to do, but they also have presented their findings in a well-written paper. The solution proposed in paper can be classified as incremental because the solution has already been there, uh, and it is similar to partitioning work and distributing it across different machines. So it is not a new solution, it is already been there. From this paper, we learn about straggler problem in cloud computing and its solution, FlexRR, uh, that addresses the problem for iterative convergent data parallel ML. It avoids wait times for slow workers, distributes their work to other workers, and helps achieve near ideal performance.